You'll remember when we talked about chemical reaction, we talked about having states of matter on all your reactants and products. And those states of matter were solid, liquid, gas, and AQ. And later, when we delved into solutions, we talked about the specific forms of concentration that go into describing a reactant or product in aqueous solution. And now I want to take a little bit of time to talk about the other states of matter, solid, liquid, and gas. We'll do that by way of introducing the phase diagram. Phase diagram is a graphical representation of all of the possible states of matter for a pure substance given particular temperatures and pressures. And generally, when we think about these states of matter or we think about state changes, we're focusing on one pressure, and that's atmospheric pressure. But of course, there are a whole range of pressures above and below atmospheric pressure. So you have in front of you the standard format of a phase diagram. It kind of makes this Y shape, where over here to the left, we're going to have temperatures and pressures where most pure substances are typically solids. In the middle of the Y there, we have conditions under which you're likely to have a liquid. And then down here at low temperatures, or low pressures, sorry, and high temperatures, things tend to be gases. Where all of those things meet, we have what's called the triple point. And triple point is really a diagnostic feature of pure substances, because every pure substance has its triple point at a fairly specific temperature and pressure. And the triple point is just the temperature and pressure for that substance where solid, liquid, and gas can all coexist in the same sealed container. When we look at individual phase changes across the lines on this diagram, we'll focus first on the solid-liquid line. Going from solid to liquid, of course, is called melting. The reverse process is called solidification. The liquid vapor line, we have vaporization. When you go from a liquid to a gas, we have condensation in the reverse process when the gas condenses down into a liquid. And then down below the triple point, where a solid goes to the gas, we have the process of sublimation. Your most likely experience of this is if you've ever been around dry ice, solid carbon dioxide. Atmospheric pressure is below the triple point for carbon dioxide, and so its solid directly sublimes into a gas. And then the reverse process is called deposition. And this is sometimes what happens when water vapor in the atmosphere condenses directly to a solid, and you get frost on your windshield. And again, as I said before, typically when we're thinking about states of matter and state changes, we're thinking at 1 atmosphere of pressure, or at fairly normal pressures. And when we cross those lines at 1 atmosphere of pressure, we have what's called the normal melting point, which is the melting point of that, or the temperature, sorry, at which that substance turns from a solid to a liquid at 1 atmosphere. And then we have the normal boiling point, which is the temperature at which a liquid goes to a gas at 1 atmosphere. You might also notice that the solid-liquid line has a fairly negligible change as pressure increases or decreases, whereas you have more of a slope on the liquid to vapor line, and so you can boil things at actually a fair number of different temperatures, which is again out of most people's normal context. But this, of course, is why you need things like high altitude cooking instructions on a cake recipe. So when, and this actually has more to do with the gases that are produced as the process of making baked goods are going to expand at different rates when the external pressure is lower. More specific to boiling, some of you may know what this image is. I'm sure if you show it to someone a little bit older, they're more than likely to be able to tell you that this is a pressure cooker. So this is a pan that seals. There's usually a rubber gasket inside that top lid. So you can seal the pan and put it on your stovetop, and then as things begin to boil rather than the steam escaping, it gets trapped inside the pan, increasing the pressure. So you can actually raise the temperature at which water boils, and so you can reduce your cooking times. It's more likely that you'll know what this is, which is a countertop electronic version of the pressure cooker, and these have become very popular in the last couple of years. It's more than likely most of you have one of these in your house. All right, so let's return to the phase diagram. So here's a specific phase diagram with water with some specific data on there. We have our triple point, which happens below 1 atmosphere. We have our normal boiling point over here at 1 atmosphere and 100 degrees Celsius, our normal melting point at 0 degrees Celsius. Up here, we have what's called the critical point, and we'll come back to that in a second. But what I really want to draw your attention to in this diagram is the scale. So this graph is not really scaled. There are just a couple of numbers here on the y-axis. We have 0.006, we have 1 atmosphere, and then we have 218 atmospheres. And this is done this way because if we were to draw this graph to scale, what you're going to end up is what's in the white box here, where most of the information below the triple point is the very, very bottom of the graph. And our 1 atmosphere line would also be fairly close to the bottom, so most of our normal experience with water would not be depicted on this graph. One of the ways to account for this, so here's a far more detailed version of the phase diagram of water. So you'll notice we have two temperature scales. We have a Celsius temperature scale on the bottom. We have a Kelvin temperature scale on the top. The right side is measured in bars, which are similar to atmospheres. And on the left side, we have pascals, which are the SI unit of pressure. And so if you look at this scale, it starts at 1 Pascal, and the next increment is 10 pascals. When we go to the next increment, we end up with 100 pascals, and then 1 kilopascal, which is 1,000. So you'll notice as we increase each increment, the scale increases by a factor of 10. And this is what's called a logarithmic scale, specifically log base 10. What this allows us to do is fit more of the phase diagram onto a sheet of paper, and to get all of those different and interesting values kind of centered on the graph without losing the detail that we want. And so this is a really, really useful way to use logarithmic scales. Here's another phase diagram I want you to look at. This is the phase diagram of carbon dioxide. Again, you'll notice that we have 5.2 bars is where the critical point happens. So 1 atmosphere is actually below. The comma there is actually a decimal point for us here in the US. Of course, European countries use the comma where we use the decimal, and decimal where we use the comma. So I'll give you an idea on what's going on there. Again, we have that supercritical fluid over here. We have the solid, we have the liquid, we have the gas, and we'll talk more about that critical point here in a second. Mainly what I want you to do now is kind of get an idea of what's going on here. When you look at the phase diagram of water and the phase diagram of carbon dioxide side by side, if you look at this solid liquid line for water, it's nearly straight up and down. Actually, if you look at it at a higher resolution, it has a slightly negative slope, whereas the melting point's actually a little bit lower at higher pressures. Whereas if you jump over here to carbon dioxide, the phase diagram for carbon dioxide, this solid liquid line has a positive slope. So that's just one illustration of how different phase diagrams for different substances have kind of this general format, but variations which are specific to that substance. So these are phase diagrams for two compounds. This is a phase diagram of an element, specifically carbon. And one of the things you ought to immediately notice here is that there are 4 segments rather than 3 segments to this particular phase diagram. And if we focus on the left here, diamond and graphite, we know that graphite is a solid form of carbon. This is what's in your pencils as pencil lead is actually carbon graphite. And of course, we know diamonds in jewelry are another solid form. So we have 2 different fairly distinct solid forms of carbon. And when you have that, you have what's known as allotropes. Allotropes are just different forms of the same state of matter for any pure substance, and carbon has several allotropes. Some of you may remember from your early elementary or middle school science classes that there is a fourth state of matter, what we refer to as plasma. Plasma is just a highly ionized form of matter. By that we mean we strip all the electrons off of the atom because you're at very either high temperatures, low pressures, or a combination of the two. And under those conditions, the electrons will strip off of the nuclei, and you'll have this kind of soup of positive nuclei and negative electrons. Some examples of some plasma over here, you have the plasma ball, which is a kind of a novelty item. It's a very low pressure environment that has a very low pressure gas in it. When you run an electric current through it, that gas gets ionized into a plasma. And that electric discharge, if you put your fingers on the plasma ball, you can track that electric discharge and move it around with your hands. A lightning strike generates enough energy around the lightning strike to temporarily convert the atmosphere into a plasma around the lightning strike. Of course, as soon as the strike is over and those high energy conditions go away, then those electrons are gonna re-adhere to the various nuclei around them. And then neon signs, another low pressure gas inside a tube that's electrified to create plasma. And if you look at this diagram on the right, you'll notice that all three of the standard states of matter, you can interchange between them depending on the temperature and the pressure. We can go back and forth between a solid and gas. We can go back and forth between a liquid and a gas. Plasmas can only happen if you've already first converted your substance to a gas. So once you are in the gas form, the process of converting to a plasma is called ionization, or stripping the electrons off. And then the reverse process is called deionization. The next bit we want to talk about on that phase diagram is the supercritical fluid. So at very high temperatures and pressures, things start to get a little weird. And you'll notice on the phase diagrams that there's kind of a fuzzy line separating liquids and gases from supercritical fluids. And that's because you have somewhat of a combination of liquid and gas properties in the same substance. So some of the features of supercritical fluid is you can dissolve things in it just like you would a typical liquid solvent. So you can dissolve solids in a supercritical fluid, but that solvent is then compressible because it behaves like a gas. Not only is it compressible, but it can have variable density. So part of it can be compressed while another part of it is not compressed. They also have fairly low viscosities, which means they have a very low resistance to flowing. So they're used for a number of industrial processes for common products that you probably use around your house. Probably the easiest to describe is extraction processes. For instance, extracting caffeine from coffee is done using supercritical fluids, although I can't imagine why anyone would want to extract that absolutely beautiful substance from coffee, but some people do for various reasons. Also, essential oils are generally created using supercritical extractions. So that's kind of slight overview on supercritical fluids. And to give you an idea on about how weird things get with supercritical fluids, when water is in its supercritical phase, it has a couple of weird properties. One, we know that water is a polar molecule, and it's under normal temperatures and pressures, it's fairly important to a lot of biological and non-biological processes that it is polar. But under supercritical conditions, water converts to be a non-polar molecule, so that's kind of weird. We also know that typically pure water is has a neutral pH, but it turns to an acidic pH as a supercritical fluid. And so we'll end here with this little fun fact that the planet Venus has an atmospheric pressure about 90 times greater than the Earth, so about 90 atmospheres. and an average temperature of about 467 degrees Celsius, so pretty toasty. And 97% of the atmosphere of Venus is carbon dioxide. So it'd be reasonable to consider that the atmosphere of Venus is probably a supercritical fluid of carbon dioxide, although given the very extreme conditions, it'd be super hard to test that out because most of the equipment that you would send in to sample that atmosphere would get destroyed under those conditions. So that's a little introduction to phase diagrams and states of matter.